Hello. Hi, good evening, everybody. Am I audible and visible?
Yes.
Yes,
Yes,
okay.
ma'am.
Great, yeah. It's 5 minutes past the scheduled time, so I think we can slowly start and maybe others will join in the process. Once again, a good evening, everybody, and welcome to today's tutorial session. I see one new face, so yeah, sorry, I was just admitting somebody. Yes, I see one new face, Vishaka. Could you kindly introduce yourself? It would be good.
Yeah. Hello. I'm Vishakha. Like I'm an architect planner, and I joined this course a little bit late. I'm catching up. I joined this urban utilities planning course recently, and thinking that like it is an essential course, facing the looking at the urban issues today's nowadays, especially floodings. and related to solid waste management. Even though I have a knowledge of this field in the planning, but I am hoping this course is kind of helping me to handle and understand the issues in quite detail. So, looking forward to this course. Yeah,
That's good.
thank you.
That's good to hear from you. Yeah. Yeah, that's nice. So it no worries that you joined late. So were you able to complete week one assignment?
Yeah, I am done with that. I am on like week two.
Okay,
Will be
then it's good to go.
catching up on. Oh yeah, week three.
Right. So, yeah, so this week we will discuss about week two assignment. So, yeah, so
Okay.
you can catch up, like, no worries. It's good you're here. Okay, great. So I think others we had met the other day. So, uh, I'll just share my presentation and we'll get started. Yes. So, screen's visible, right? Yeah. Okay. So yes, so before we begin, I had two things to clarify. That is last week's discussion. We had two things I said that I'll get back. So the first one was there was when we discussed about decline in groundwater levels, there was a discussion on how illegal extraction leads to decline in groundwater levels. So there was this question on whether there are any existing rules which needs to be followed on groundwater extraction. So we had a small discussion on that. So currently in 2020, a rule has been formulated, and 2022 it's been abridged. In 2023 again, there is a small abridgment on that. So so theoretically there are certain rules which have been in place, which gives for each building type, if it's for industrial use, residential use, mining use. So for each category, there are certain rules that needs to be followed while building a well, and the percentage of water that can be extracted, there are certain rules on that. So before we build something, we need to get a no objection certificate from the authorities in order to build something. So this has to be accounted, so then we know that there is a well in this particular location and this much of water is being drained from there. But again, the only problem right now what we're facing is theoretically these rules are in place, but we do not have a very well established monitoring mechanism, and rules are being formulated in this in order to have a good monitoring mechanisms and to prevent this illegal extraction. So I can share with you that link where the government notification is there. So I'll just share the link because this was a very interesting question, a very practical question which was asked, which is uh, one of the major issues. So this is the Government of India's page where you have the guidelines. So there are different guidelines for bulk water supplies, abstraction of saline groundwater, then to regulate the control or regulate groundwater extraction. So all these you can see, and it's again getting amended also. So yeah, so you can go through this. So this was one thing. Then the second question was on bioremediation. So we had discussed about bioremediation, and in the discussion, I think it was suggested or we there was an opinion saying that bioremediation is only used for organic. Yeah, so bioremediation is only used for organic components, but that's not the case. Bioorganisms or algae are used in order to reduce both organic and inorganic components. Both. It's not just organic components. Both inorganic and organic components are detoxified or reduced into simpler forms, and this is used as a wastewater treatment process. So the process is named bioremediation because bioorganisms are used, but both inorganic materials can also be reduced. So because of that, there was one option which we had where desiltation is part of bioremediation, which was correct because desiltation involves inorganic components, and bioremediation can reduce desiltation or can bring in desiltation also. Okay, so that was about last week's two questions which we had uh, kept pending. So with that, I think we will begin this week's tutorial. So yes, so to introduce myself to the new person who's there. So I'm Jeslu. I'm a Prime Minister's Research Fellow in IIT Kharagpur. I've been working with Professor Pandit for the past 4 years. So this week we will look into these are the topics which we discussed in this week. So we looked at water demand prediction and water demand prediction and management. So in this we saw how can we predict what are the types of water. Then in the next lecture we saw what are the types of water demand, what is it being used for, uh, for fire demand, for drinking, for water, domestic water supply. So for all these elements we saw what are the different types of water demand. Then in the lecture after that we saw into what causes fluctuations in water demand, what are these special and temporal factors which causes fluctuations in water demand. And in the later lecture we saw into the role of government. So how water is supplied, who monitors what is the state responsibilities, what are the center responsibilities, are there any local bodies which regulate water. So all these roles of government we saw. And finally in the last one we looked into what are the costs, like is there a there's fixed cost, there is indirect cost, direct cost, indirect cost, fixed cost, maintenance cost. Then we also saw how do we set tariffs. What is it, a flat tariff, or is it a block tariff, or is it a volumetric tariff? So all these aspects we saw in our last lecture. So based on all this, we will discuss certain questions. So these questions have been taken from previous year's assignment, so that it will help you to solve this week's assignment. So yes, so with that, let's get started. So this, all of you know, we'll go question by question, and we'll stop after every question. After the whole session, we'll again have a question answer session. And yeah, so most important point is that if I'm stuck at any point, please feel free to let me know, speak it out or put it in the chat box, because I might not know. One sec, somebody wants to join. Rest. Okay, so let's get started. So the first question is, which of the following causes seasonal fluctuation in water demand? Uh, okay, so I think we can just omit the first one, the housing typology one. That was supposed to be an option, but like let's uh, let's omit that one. I think I made a mistake. Yeah, this one. So first one is income, temperature, population, and heat heat wave. So we are talking about seasonal fluctuation. So okay, firstly, wow, why do you think there are fluctuations in water demand? Like seasonal fluctuation is one reason, yes. What are the other fluctuations that can be there? Anybody?
It could be due to the water usage behavior of the persons, and
Correct.
then there could be some high temperature heat waves.
Mm-hmm. Right. Yes. So there are many factors, like it can be behavioral factors. So seasonal comes into the environment factors because of the variations in environments. Then it can also be based on within a day itself. Like you can have different usage, like based on the peak time. Like you need it for certain period of time, so there can be fluctuations in the peak time. So again, this is also linked to the behavior or the activity that the person is doing. Then also based on the population. Like if there's suddenly if there's a population growth, there can be so by when there's a special variation in the region where the water is being used, there can be a fluctuation in water demand because of that. Even household type, the different levels of housing, like if it's an affluent society, you might use more water, whereas if people cannot afford a lot of water, then maybe they may use less, or maybe the usage would be a bit different from so based on the economic value of the place. So there are so many factors which causes fluctuations in water demand. So here mainly we are talking about seasonal fluctuation. So to talk about water variations in water demand, we can say that there are temporal variations and there are spatial variations. So in temporal variations comes all this wind speed, temperature, water prices, population. So by temporal, what we are talking about is something which is related to time. So with time, it's changing. For instance, in 2000, if the water demand was say A, then in 2010, the water demand is increasing. So with time, it's increasing. So that there is, or with time, there are certain factors. And why is this increasing? Because there are certain factors which are increasing with time. So it's not just year, like in within a year itself, like in 2000 itself, in January it might be something, in December it might be something else. So which means with time there is a fluctuation, and that comprises of the temporal variations. Now there can be spatial variations also, which means with the space, like for instance, in one region the education level or the build up area in one region will be different from a different region. So because of this, these two regions will have different water demands. So this is a spatial variation which is there. So all these factors constitute the spatial variations. So when we are talking about season, we are mainly talking about what? Is it a temporal variation or is it a spatial variation?
Temporal, no?
It's a temporal
Temporal
variation.
variation.
Correct, correct. Very good. Yeah. So it's a temporal variation. So let's go back to the option and see which of these is a temporal variation that we have. So income, is it a temporal variation or a spatial variation?
Spatial.
Income, yeah, it is a spatial. Income is a spatial variation, but with time also, the income of the family can also change. So it can be included in both. So it is so if you can see the slide, it is included under a temporal variation because over the years, the income of the family can also change, and uh, because of this, their water usage. One sec, somebody has joined. Yeah, because of this, the water usage behavior may also change. But when we're talking about seasonal fluctuation, income will not be part of it because with season, we can't say that every year at this particular season, the income's gonna change. It's not gonna change. So income is not the answer here. Temperature is, will that change with season?
It's not.
Yeah, and it changes with season and it causes seasonal variation. So the question mainly asks us what causes seasonal variation. So yes, temperature causes seasonal fluctuation. And population, will it cause seasonal fluctuation?
No.
No, population will not. So population again is a spatial factor, and it cannot change the seasonal with seasons. The population is not gonna change. So that's not the answer. And the last one, heat wave, does it cause a seasonal fluctuation?
Yes, yes.
Okay. Anybody feels it doesn't cause a seasonal fluctuation?
It lasts for maybe 2 3 days, 1 week, so it causes immediate fluctuation, I think.
Correct, exactly. So we cannot claim that heat wave causes a seasonal variation. So seasonal variation, by seasonal variation, what we are talking is that in the month of summer, there is suddenly an increase in water demand because people need more water, or it's very hot, so people might take bath at least 2 times a day. So there is more water consumption during that time. And in winter, suddenly the usage is reducing. So let's imagine that in a region, such a variation is or a fluctuation is happening. But heat wave is something which is more spontaneous, as rightly pointed out. It can be there for a certain duration, but it's not necessary that it should be there for the entire summer duration, or it should be there every summer. It need not repeat every summer also. So it's a sudden variation, or maybe a weather change, or a more dynamic variation which is happening. So we cannot say that that causes a seasonal fluctuation in water demand. So yeah, so here this is a tricky part. So it might look like heat wave can cause seasonal fluctuation, but it doesn't, because we are talking about the main definition of something which recurs every year. So coming back, yeah, so heat wave cannot. So the answer is temperature. So in this, it's temperature causes seasonal fluctuation in water demand. Okay. So any doubts in this question? Okay, very good. So let's proceed on to the next question. So this is a numerical. So I would suggest all of you to take your calculators and we'll work it out together. So the question asks, estimate the total fire demand for a small city having a population of 45,000 if three fires break out in a day and each fire stands for 3 hours. So we've been asked to find the total fire demand. This is what we need to find. And we know, so I'm just writing down whatever we know. So we know the population is 45,000, and we know that the number of fires is we have got three fires break out in a day, in one day, three fires, and the duration of the fire also we know duration is for information which is given to us. So now, how do we find fire demand? Like I'm sure all of you have gone through the lectures, right? The video lectures. Okay, I'm assuming that all of you have gone through the video lectures. So we learned three methods of estimating fire demand. Can somebody give out any of the method which you remember? Okay, so let's say what is the significance of population? So based on the population, the number of people who are residing in a place, the formula that we use in order to calculate the fire demand also varies. So we have learned three methods. So the first method is that if the population is less than 50,000, we will go by this method where Q is equal to number of fire into the discharge in minutes into the duration and divided by the total population. So this will give us the water demand in milliliters per day. So we will come to that. And the second one is that if the population is more than 50,000. So if it is more than 50,000, then we will directly go by this formula because the quantity is large. So we can estimate it because we're estimating it for a larger group. We need not be very particular because there's more diversity is allowed in that case. So we'll just go by a very blanket formula where Q is equal to 100 root P, where P is a population in thousands. And the last one, we learned Kirchling's formula, where we use 3182 root P. So these are the three methods which we discussed in our lectures in order to estimate fire demand. So over here, which method would be suitable?
Method one.
Method one is suitable, yes. Why? Because, why again? Why is method one suitable?
Population is less than
Population.
45,000. 50.
Correct, correct. Both of you are right. Yeah. So population is 45,000, which means it's less than 50,000. So now if it is equal to 50,000 also, we can go by the first one. In fact, if we go by the first one, it'll always be correct only. But in order to reduce the complexity, like for instance, here we only need the population. We need not know about the discharge or the number of fire or the duration of fire. So that's why we're using a second formula where we just have limited information and we can use the second formula. So we'll go by the first formula. So if that's the case, yeah, so we are using this. So if that's the case, let's see if we are writing the first formula. So let's do this together. So Q will be equal to the number of fire into the discharge rate. So discharge, we should keep in mind that the discharge that we are talking about is in minutes, and we are multiplying it by the time in minutes or the duration, which is a duration actually. So duration, so that is again in minutes, and this whole thing. So if we want to find it per person, whatever we have, we'll have to divide it by the total population. So that's the formula. Yeah, that's the formula that we're using where we are finding it per person. But okay, let's just put it as the formula itself. So let's say what is the total number of fires? So there are three fires. And what is the discharge rate? Let's go back to the question. The Okay, so discharge rate is not given, discharge in minutes is not given in the question, but we can always assume a discharge of around so there are standard discharges in the lecture which we learned. So the standard discharge of a stream in the lectures we have seen that around 1,100 liters per minute, and usually there are three streams from a fire hydrant. So each stream will have 1,100 liters per minute. So this is one assumption that we need to make, that it should be 1,100 liters per minute. This is based on the standard that we follow, and we are assuming that we're using one stream, one jet stream in order to fall. But if sometimes in the question it may say that the discharge is around 1,000 liters per minute, so if that's the case then you use that, but if nothing is given it should be 1,100 liters. So we are taking 1,100 liters per minute. And the duration, we know that it's the duration is for 3 hours. So 3 hours into, because the time has to be in minutes, so into 60. and divided by the total population of 4,500. So I'm not going to solve this right now, like let this be. So now if you look at the the options, so this one gives us per capita, like for per person what is the fire demand. So but in the question it's just given kiloliters per day. So which means we don't have to find it per person. So which means we'll again the whatever value that we're getting, we need to, so eventually we need to convert it to kiloliters per day. This is what we need to convert it to, or let's say liters per day. So this is going to give us in LPCD, liters per capita per day. This is the one that we are going to get from this one. Like the unit of this is LPCD, liters per capita per day. So to convert, I'm sorry, I'm going, yeah. So to convert this into, if we are removing this per capita out, we need to multiply it by the population. So again, so it'll eventually be 3 into 1,100 into 60 divided by 4,500 into 4,500. So this will get cancelled out. So now we can solve this, and yeah, how much does this work out to? How much does that work out to?
5,94,000.
Yeah, so that will be 594, yeah, 1,000 liters per day. So the question is in kiloliters per day, so it will be 594, right? So that's there in our option B if we look. Yeah, it's 594 kiloliters per day. That's the answer. Any doubts in this question? Okay, so let's proceed on to the next question. So this is also a numerical. This is a very simple numerical. So it just says, give the total fire demand for a city having a population of 9 lakhs using Kirchling's formula. So they've mentioned use Kirchling's formula. So it's a direct formula application. So so the population is given to be 9 lakhs, so which is 9 into 10 raised to 5. Now, what was Kirchling's formula? So Q is equal to 3182 root P. So if I write it as 3182 root 9 into 10 raised to 5, is this correct? Is that the right method? Okay. So one factor that we need to consider here, yes, somebody was saying something.
Uh, Population, we have to check whether it was in thousand or lakhs. I'm not
Correct.
sure about the formula.
Correct. Yeah. So you're absolutely right. Very good. So if you have to use Kirchling's formula, the population should be in thousands. That is the only requirement. So like the previous formula, we said the time should be in minutes. So here the population should be in thousands. Only then this. These are all empirical formulas, right? So if the unit changes, then or if the factor that we're taking changes, then we'll get a wrong answer. So it should be in thousands. So here it's given in lakhs. So now we have converted it, but we need to cut. So for every 1,000 population, we need to say, so we'll divide it by 10 raised to 3 in order to make the population into thousands. And then if we apply, we will get the correct answer. So this will be, yeah, so this and this will go, it should be 900. Let me just put in 900. Yeah, so what does this work out to?
95460.
95460. Yeah, so that is there in as option D, right? Yeah, 95460 liters per minute. Okay. Any doubts in this question, anybody? Yes, let's proceed. So yeah, so this was that. Yeah. So yes. So now we're going to question 4. The question is that, question asks, maximum hourly consumption when average daily consumption is 300 LPCD is dash LPC. So they have asked for maximum hourly consumption. So again, what does LPCD stand for? I just explained.
Liters per
Liter per
capita per
capita.
day.
Yeah. So here again, because this is maximum hourly consumption, the day is being taken out, and it's us in the maximum hourly consumption from when average daily consumption is 300 LPCD is. So we have learned certain, again, before we go into that, why do you think there is a maximum hourly consumption, or why do you think for every hour there is a variation or there's a fluctuation? We just discussed that. So there can be several factors leading to it. It can be a habitual factor, climatic factor, there can be seasonal variations. So based on that, so if you take a time within a day itself, in an hour there can be certain peaks and certain lows. For instance, when at morning 8 a.m. to 9 a.m. there can be a peak because people are going out or they get ready to go out, and then again evening then it again drops. In evening there's again a peak because people are coming back and they're using the water in the evening time. So based on this, we that for every hour there can be a variation, and we've derived certain general factors which can be used in order to, sorry, yeah, so we've devised certain factors which we multiply these factors with the average consumption in order to find the peak values. So does somebody remember, if you want to convert the average annual consumption into maximum daily consumption, what's the factor that we use? It's how many times. So maximum daily consumption is how many times the average annual consumption.
2.7 or 1.8.
Okay. Uh, okay, so let's go that you're partially right. So let's go into that. So it's good to remember this. So maximum daily consumption is around 180 times more, 180 percentage of the average annual consumption. So this something which is given in LPCD, which will come into the maximum daily 180 times the average annual consumption. And the maximum hourly consumption, which is our LPC, is around 1.5 times or 150 percentage of the average daily consumption, right? So now if you want to find what is the maximum hourly consumption of the maximum day, so in the entire year, if for instance, let's say June 10th is when you're consuming the maximum, for that, and at 10 a.m. for in an entire duration of the day, 10 a.m. is the maximum hourly consumption. So for June 10th at 10 a.m., what will be the maximum consumption? So we'll have to multiply both 150 times 180 times the average hourly consumption. So that's from where we get the 2.7 when you're multiplying both. So yeah, so this 1.8, 1.5 and 2.7, it's good to remember those. So here the question asks what is the maximum hourly consumption, which means we are going with this one, which is the maximum hourly consumption given the average daily consumption. So let's look, is that what is given? Yeah, so we have the we are directly given the average daily consumption. So it's a direct formula application. So we can say the maximum hourly consumption, yeah, maximum hourly consumption would be around 150 percentage of so one thing that we need to look into over here is that the average daily consumption is given in liters per capita per day. So liters per capita per day it's given, and here we need only maximum hourly, it is per capita, so we divide this by 24. So this is something which we might forget to do. So whatever we've got, we have to divide it because there are 24 hours. We have to divide it, and one second, let me admit somebody. Yeah, right. So yeah, so you have to divide it by 24, and yeah. So let's do this calculation. So this will be 1.5 into 300 by 24. How much does that work out to? How much does that work out to?
It is 18.75 marks, option C.
Correct. 18.75. So here, yeah, it's been given in a range. So 18.1 to 19. So option C will be the correct answer. Right. Any doubts in this question? Anybody? Okay, great. So let's proceed on to the next question. So this is a continuation of the previous question, where by continuation I meant it's very similar to the previous question. So the theory will be similar. So the maximum hourly consumption of the day with maximum daily consumption when average daily consumption is 200 LPCD is dash LPC. So, okay, I would suggest one of you to tell me how we go about this question because we have already discussed the theory, so it's going to be easy. Which formula would we use? What factor? Do we use 1.8, 1.5, or 2.7? So what we have been got, we have maximum. We have to find the maximum hourly consumption, okay, and we have the maximum day. Okay, we have to find the maximum hourly consumption of the day with the maximum daily consumption. So it's maximum of the maximum hour of the maximum day when the average daily consumption is given. So what's the factor that we use?
2.7.
Correct, 2.7. So why again, just to explain, we will use 1.8 in order to get the maximum daily consumption. So from the average consumption, and again we have to divide it by 24 because it's given for an entire day. And to get the hourly peak, we will again multiply it with 1.5. So this works out to 2.7. So it's 2.7 into 200 by 24. So how much does that work out to?
22.5.
22.5. Very good. So that is there as option D, 22.5. Great. So any doubts in this question? No doubts. Very good. So we can proceed. Yeah, so that was a fairly simple question. So yeah, so now we're going to question 6. So this is again not very difficult. So identify the false statement concerning water supply. Four options are given. First one is 24-hour supply decreases wastage due to leak reduces 24-hour supply decreases wastage of water due to leakage. B, there is constant pressure in the distribution system in 24-hour supply. C, maintenance requirement for joints and meters is comparatively more for 24-hour supply than intermittent supply. And D, metering reduces water pressure drop. So, yeah, so this is regarding water supply. Mainly, it's talking about 24-hour supply and intermittent supply. And what do we use? So, let's start from the last option. Option B, is that right or wrong? Does metering reduce the water pressure drop? Any idea? Okay, so this is, yeah, I mean, yes, somebody was saying something.
Maybe I'm not able to understand this point, but I think it is false.
You think it's false. You think metering does not reduce water pressure drop. You feel that it should be
Yeah.
constant. Metering does not affect the pressure drop, is what you're saying.
Yes, yes.
Okay. Anybody, any difference of opinion? Uh, Ma'am, I think Revati, like you want to add something?
No, 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 madam. It's
Okay. Yeah. Okay. So, yeah. So I think this part, maybe in the lecture, we've not discussed in detail on how metering affects water pressure. So we know that when there's 24-hour supply or continuous supply. So let's start from. So when there's continuous supply, there's continuous water which is flowing through. So there's a constant pressure which is there. So now what metering happens? The problem is that we're introducing another element onto this water supply or the pipeline in order to, when you're metering, you're introducing a meter onto it. So because of this, there is a difference in, or there's an alteration in pressure drop because there is an external element which is there. So when there's metering, there is a pressure drop. Metering reduces water pressure drop. So that's actually a right statement. When you're introducing something external or a meter into our pipeline, because of that, there's a pressure difference which exists. So maybe this we have not discussed in detail in the lecture. So that's why a confusion is there. So yeah, so that answer is actually right. Now, option C, maintenance required for joints and meters is comparatively more for a 24-hour supply than an intermittent supply. Is that right?
Yeah, right.
It is right, ma'am.
It is right. Why? Why is the statement right? Why do we need more maintenance?
Because the
To ensure
water is always there, then we have to maintain it properly so that there is no leakage, no wastage.
Correct. Correct, absolutely right. Yeah, so maintenance is more, uh, you need to maintain more when there's a 24-hour water supply. Now let's go back to option B. There is constant pressure in the distribution system in 24-hour supply. Is that right?
Correct.
Correct, yes, because that's what we discussed. So because there's always water which is flowing, so there's a constant pressure. And option A, 24-hour supply decreases wastage of water due to leakage. Is that right?
False.
It's false. Same thing. Like, see what we discussed. If there is a small leakage, then if it's a 24-hour supply, water will just keep going. Whereas intermittent supply, only for that hour when water is pumped, there will be leakage. So the false statement here is A, 24-hour water supply decreases wastage of water due to leakage. Right. So shall we proceed on to the next question?
So I have one doubt regarding the D statement.
Haha.
Maybe I'm not sure, but the statement is metering reduces water pressure drop.
Haha.
So I think the statement should have been metering reduces water pressure
Correct.
in the pipe, water pressure in the pipe, not the water pressure drop in the pipe.
Correct, correct.
Uh,
That is a very,
this
yeah,
could
that's a
be
valid
checked,
point.
maybe. I
No,
don't
no,
know.
that is a valid point. Yes, so there is a defect in that question. It reduces water pressure only. Does that water pressure drop? Yes, it because there is already a drop and it reduces water pressure drop. No, no, it's right. Sorry, I'm sorry. It is correct only because there is always, so whenever water has to flow, there is a water pressure drop. For instance, from here to here, there's always a pressure drop, and because of that, water is flowing. So yeah, so if it says it reduces water pressure drop, it is correct because there is an external element which is coming in there. There is already a drop happening here. So because of this, there is a reduction in the water pressure drop for which it was initially designed for, which will lead the water to flow. So water always, like when there is a difference in pressure, that's when it keeps moving, right? Like in the pipeline. So there should be a pressure difference. So that pressure, water designed pressure drops. So because of the metering, it reduces the water pressure drop. So I think the drop is very important over there. Yes, it is because it's mentioned. It reduces. Yes, it's required. Is that clear? No, that's not clear.
I think the water flows from the pipe due to
Haha.
the pressure of the pumps.
Yes.
So when the water flows,
Mm-hmm.
the pressure reduces due to the friction losses, or when it goes a long distance.
Mm-hmm.
So the pressure, the water doesn't flow because of the pressure drop. I'm not sure about the statement, but I think maybe it could be checked.
Okay, yeah. So in pumping itself, there are certain heads, pumping heads for which we design. So which you will see in the next lectures. So yes, so the pumps are designed in order to create that head or the pressure difference. So yes, so in this particular statement, when they say that because you're introducing a meter, the pressure, water pressure drop, which is there in the pipe, that reduces. That's right. Now, how do we design, or how is water pumped? How do we design the pumping mechanism? What should be the pressure difference or the pressure head that we are designing it for? That part we will see later, and then I think it would be clear to you when we are dealing with water pumps, which I think is there in your lecture 3. I'm not sure, 3 or 4 somewhere, week 3 or week 4. It's coming soon, and then it would be a bit more clear. Okay. Any doubts? Any more doubts in this question?
Yeah, okay, maybe it will be clear then. Okay.
Yeah, okay, fine. So let's proceed on. So yes, so question 7, it's on coincident draft. So coincident draft for a city with a population of 1.5 lakh population, okay, with an average water demand of 200 LPCD is, and they've asked to give the answer in milliliter MLD, like milliliters per day. Okay, so let's let's and yeah, so calculate this one, use Kilchin formula to calculate water demand, that is also given. So first we're talking about coincident draft. So how do we calculate coincident draft? There are two methods to calculate coincident draft. So coincident draft, or the total draft, can be, the first one is that we take the sum of the maximum daily demand plus fire demand. This is the first one, or we can go for the maximum hourly demand of the maximum day, which the 2.7 factor which we used of the maximum day. So these are the two methods, and in this, how do we select? We take the maximum of this both, like whichever is maximum. Either it can be maximum of maximum daily demand plus the fire demand, or the maximum of the hourly demand for maximum day. So this is how we are using. So this one we will be using Quichling's formula when we're calculating the fire demand. We would need it. So let's calculate both and then see which is the one that we need to take. So in the first one, we need to find the maximum daily demand. So how do we find the maximum daily demand? What is the so again, yeah, let's just go back. The question is given, the average water demand is 200 LPCD and the population is 1.5 lakhs. So let's just write that here first. So the population is 1.5 lakhs and the average demand is 200 LPCD. So this is what is given. So our so let's go. What will be the maximum daily demand? Maximum daily demand. Can somebody say what will be the expression for that? Yeah, we just discussed this.
2.7 times average demand.
Maximum, no, we are only looking at the maximum daily demand. We are not looking at the maximum hourly demand of the maximum day. We're just looking at the maximum daily demand. So what is the factor for that? It's not 2.7.
1.8 now.
1.8, correct. So for maximum daily demand, it's 1.8 into, so again, this is given in LPCD, which means liters per capita per day. So, and here the question is asking us to find in million liters, or basically liters per day, million liters per day, which means we have to get rid of the per capita over there. So we have to multiply it with the population. So if there are, for 200 LPCD, which means for a population of about 1.5 lakhs, it will be 200 into 1.5 lakhs. So 200 into 1.5 lakhs. So this is the population. So this is the expression that we have. So how much does that work out to? That's a simple calculation. How much does that work out to?
5 crore 40 lakhs.
40 lakhs. Okay. In million liters per day, how much is it?
54.
Yeah, 54, correct. Yeah, 54, correct. It is 54 million liters per day. So this gives us the water demand. Now we have to find the fire demand also, or the daily maximum water. Now the fire demand. So fire demand, we can directly use Kitchling's formula. So what was Kitchling's formula? That was 3182 root of population in thousands. So here the population was given in lakhs. So again, we'll have to convert it to thousands. So divided by 1000. Right. So how much does this work out to?
Thirty-eight nine seven one.
Yeah, so you will get
0.38.
38971 .3, let's say 0.38. So yeah, I'll put it as 38 itself. What is a unit? In Kitchling's formula, what we are getting is, what is the unit of that? what we're getting in Kuchling's formula is always liters per minute, because we saw, like in fire demand, we said the time is in minutes, the population is in thousands. So here what we're getting is liters per minute. And what we need is million liters per day. This is the requirement. So we need to convert. So in 1 minute, if this is the requirement, we'll have to convert it into 1 day. So firstly, we'll have to convert minute to hour and then hour to day. So this will be uh, before doing that, let me convert this into million liters. So I'll just take the decimal points. So it'll be 0.03971 million liters. Now I'm converting it into uh, 24 hours, and each hour, because it's in minute, so into 60. So what does that work out to?
56.12.
56.12. So approximately we can put it as 56. Let's just take it as 56, because for ease of calculation, 56 mlt, million liters per day. Right. So now if we want to find, like, let's go back to the formula. So if this, for first formula, it should be the sum of maximum daily demand plus fire demand. So we are adding Q1 and Q2. So Q1 plus Q2 is equal to 54 plus 56, which is right. So this is what we got from the first method. Now let's go to the second method, where we find the maximum hourly demand of the maximum day, like maximum daily demand. So what's the factor for that? What's the factor for that? 1.8 to 1.5, 2.7.
2.7.
2.7, correct. 2.7 into our 200 LPCD. Now we have to convert it into the population. So because we want it in MLD, we are doing the same thing into 10 raised to 5. Now we also want it in, uh, we have to divide it by the number of hours, because this is for the maximum hour that we are looking forward to. So yeah, so how much does this work out to? Yeah, so one thing, sorry, yeah, we are doing this. So this is the standard tendency that we have. We divide it by 24 in order to get it into the number of hours. But as we are saying, we are looking at MLD per day, which means we did not do that. So eventually we'll again have to multiply it by 24. So let's not do that portion, because our unit is MLD. So only this much would be required. But by standard formula, the previous question, we always divide it by 24, because we want to find the maximum hour, the demand for the maximum hour. But here we are looking for MLT. So we are again multiplying it. So I hope that's clear. So yeah, so just to put it, it would be 2.7 into 2 into, I'm taking this 10 raised to 7 into 1.5. Yeah, I missed that. Yes, so how much does that come out to?
81 MLD.
81 mld. Correct. So which one will we choose? What is a coincident draft?
110.
110. Yeah. So basically we have a choice between maximum of 110 and 81. So we will choose 110. So we use the first method. So is that there in our option? Yeah, 110 is there in our options. Let's go back one sec. It's stuck. Yeah. So 110, option B, 110 is the answer. Any doubts in this question? Okay, so let's proceed further. Question 8. Water demand is mostly inelastic in terms of income, water price, household composition, none of the above. Firstly, what do we mean by elasticity or inelasticity? Any observations, or and what do you mean by inelasticity?
Doesn't vary with.
The tendency of being flexible.
Yes, the tendency of being flexible. Yes, that's the normal definition. But as Galip said, it doesn't vary with. So in the aspect that we are talking over here, we are talking about water demand being inelastic, which means, uh, okay, inelastic means there is, okay, so if we have a factor X and we have something contributing, so X is contributing towards Y, and if Y is our water demand, now, if x is changing, if x increases, if y also changes, then it is elastic in terms of x, because whenever x is changing, y is also changing. But even when x is changing, if y does not change, then it is inelastic in terms of x. So here, that's what we want to find. If our water demand is y, then which of these x's, or which of these for which of these factors is water demand or water consumption not changing? So let's go option by option. With change in income, will there be a change in water demand?
Yes.
Yes, because this we've discussed. Like with the more affluent societies tend to use more water, so there would be water is elastic in terms of income. Water price, will
No,
it? Why
it
no?
won't vary
Why?
because whatever be the price, people tend to use whatever the water is required for them.
Correct, correct. So yeah, so that is uh, to an extent or to a lot of extent, water price does not affect water demand because, as you rightly said, it's for the basic needs. So even if it is really expensive, people will have to will have to use it. But some amount of wastage can be reduced. But here we are talking like people will not unnecessarily waste water if it is too expensive. If they're paying for it, then that responsibility would be there. But here we are mainly talking about demand, which means we are talking about the basic demand. So yes, so it is inelastic in terms of water price. Whatever the price is, we will eventually have to pay for it because it's a basic need. So yes, so this answer is correct. This is wrong. Let's look at the other options also. Household composition. Will the water demand change with change in household composition? Yes, it will change because
Yes,
correct. Yeah, it will change because more number of people, they would per capita water consumption. If you still have a fixed per capita water consumption with more number of people, you will consume more water. So household composition also, and yeah, none of these. So yeah, so the answer is B, water price, which change in water. So water is mainly inelastic in terms of water price. I think in the lecture also we have discussed this in detail a bit. So let's go to the next question. Which of the following is not an example of macro scale interaction concerning water demand? So before we attempt this, let's look at what is macro scale and what is, if not macro scale, what is the other one which is there? So what do we mean by macro scale interaction? Okay, so what is it? There's yes, yes, sir. Yes, sir.
Something which has something which has impact on national level.
National level, yes, right. Yeah, national level or mainly at an environment level. It's not very personal, but it's more of for the community or for the environment that you're in. So at a larger scale. So you have a macro scale, and along with that, we also have a micro scale also. So there are so here we are asked about mac. So before we proceed, yeah, let's look at what is, yeah. So you have a macro scale, which is at a larger regional, municipal, or a community level, or as you rightly said, at a national level or at a global level. So all that comes under the macro scale. Then we also have a micro scale, which is at a very individual household or a small uh, at a very very small level. So by the name itself, it's a micro level. So here we've been asked about which of it is not an example of macro scale interaction. So let's look at the options. Water resource planning, is that a macro or a micro scale level?
It is a micro scale.
Water resource planning, is it okay? um
macro.
Macro.
it's macro. uh okay, why is it macro?
Uh, we can cite an example of, let's say, Ganga River.
Right.
It it passes through various states. And if one state is planning for some municipal project,
Hmm.
so water resource planning comes to play because every state has some share, some sort of share to which
Okay.
they are limited to use.
Good,
So
good. Yeah,
I think it
that
is
yeah, that's very good. So just to pick out few keywords from whatever you said in order to cite this. So you said that yes, every state has a responsibility. It goes through different states. There's a state government policy which is put. So all this show that there is an authority or at a community level or at a regional or a municipal level or at the state level, there is some responsibility or some impact which is there because of this planning. So exactly. So all these resource planning or policies or allocation, all these comes under a macro scale because it doesn't consider it not only considers a single individual, but it considers people or a population at a large. So when you're talking about micro, it'll be at a very personal level. It'll be like your backyard or your well or something very individualistic. This is not a resource planning is at a municipal level or is it at an authoritative level, and it is not close to a small individual or a household. So that itself explains it. So yes, so it's not so this is an example of macro scale, which means the answer. So this is actually an example of a macro scale. So here they've asked for not an example, so this is not the right answer. Now the option B, change risk assessment, is that macro or micro? Change risk.
Macro.
macro.
Macro. Yes. Why? Again, the same thing because it's a risk assessment. So, which means it's not close to an individual or a household, but it's for a community at a large. So, it is a macro scale, which means it's not the answer for this. Option D, human impact. Option C, human impact on hydrological systems. Macro or micro?
Macro.
Macro. Same explanation. So, yes, macro. So, it's wrong. Now, the last one, household ownership of water consuming appliances.
It's micro. I
It's
guess it is the answer. It is micro.
It's micro, yeah. So that's the answer because again, it's talking at a very household level. So household ownership of water. So in one household, how many water consuming appliances are there? So that's something which can be controlled only by the household, and all these macro level planning will not have any impact on it. So this is not a macro scale, which means it is not an example. So this is the correct answer, option B. Right. So let's proceed on to the next question. Question 10. According to IS 1172/1993, what is the minimum amount of water for economically weaker section of population considering supply through a stand post for communities with population up to 20,000? This is a direct IS application uh, uh, question. So, anybody, any guesses on what's the answer for this?
100.
100. Okay. Any more guesses?
I can guess normally. It's 60 LPCD. It's LPSD.
It is 60. Okay. Anybody else? Any other difference of opinion? Okay. So let's look into the theory, what we learned. So, yeah. So, yeah. So this is what we learned for domestic water demand. So for communities with yeah, so water supply through a IS as per IS 1172/1973. Water supply through a stand post is the minimum water supply should be 40 LPHD. Now, 100 is when the communities with a population of, so this is for the population up to 20,000. For a population greater than 20,000, up to 1 lakh, and with a full flushing system, it is 100 to 135 LPCD. So here the question specifically asks for a population of 20,000. So for a 20,000, the minimum is 40. I understand why the confusion of 100 came, but that was for an increased population for about 1,000, uh, sorry, for 1 lakh population. So here the question mainly asked about population up to 20,000. So 40 LPHD is the answer for this. It's a direct national building code question. So I'm proceeding further. Question 11.
What is the stand post? What does stand post mean?
Oh, right. Sorry, I forgot it. So, if you have in certain places that where there is no public water connection system, you might have seen that there are these certain posts or pumps from which it can be a hand pump, or it is a post from which water is usually drawn. So, in most of the villages, you might have seen a hand pump. It's something like this where you use and you pump water out of it. So, it's basically it means that in a region there are certain locations where there is water available in most of the cities or more developed places, water is available to every household, right? It's a pipe system. But here, through a standard stand post, so there is no water connection to every household, but people will have to go to the stand post in order to draw water and then come back. So that's a stand post. A very common example is a hand pump, which is seen in most of these cities. So it has something like this where you pull it down and then you so this is mainly used for drawing water from the wells. So this is one example. So here we are talking about when you're supplying it through a post and from that one particular location where water. So this is not an example of pumped water collection, but I was just saying like in one region there will be one stand post and from there water will be supplied. Whereas household connection, it will vary. Household connection means there's a pipeline supply to every household. Right. Is that clear?
Yeah, okay.
Okay. Let's proceed further. Question 11. Dash identifies the areas with higher exposure for water related risks. So we have water security, water risk, water demand forecasting, water resource management. Any guesses? Okay, I think it's a very straightforward question. So, the what identified areas with higher exposure to water-related risks? So, I think from the question itself, it's kind of clear. So, will it be water security? Will water security identify areas with higher water risk?
No.
No, yeah. So it's not water security. Water security mainly stands for conservation of water or that we do not overuse water. And water risk, yes, water risk is one possibility because we identify areas which are where there's higher exposure of risk. That's one. But let's look at the other options also. Water demand forecasting talks about what will be the future demand so that we can plan our pumping systems, our water supply systems, pumps, etc. accordingly. And water resource management is mainly used in order to allocate water resources. So between different states or between different regions, in order to allocate the resources, we use water resource management. So the answer to this is water risk. Water risk identifies the areas with higher exposure to water related risk. That's a very simple question. Let's proceed on to the next question. Which of the following factors contribute as an explanatory variable for predicting spatial variation in water demand? So this is a continuation of the first question which we learned. So we saw there was spatial variation, and what was the parallel to spatial variation? There was temporal variation. So this is what we saw in the first question we discussed. So there's always spatial variation and there's always spatial variation and there's temporal variation. Spatial variation is something which changes with respect to the spatial location or the geographical location, and temporal variation is something which changes with respect to time. So the question mainly asks for which of the factors contribute towards spatial variation. This is what is asked. Yeah, predicting the spatial variation. So let's look. Temperature, is it a spatial factor or a temporal factor?
It's a temporal factor.
Temporal factor. So this does not contribute. Now contribute as an explanation. Yeah, spatial water demand. Correct. Now income, is it a spatial or a temporal?
Again,
Temporal.
Income is also yeah. So income is also a temporal one. So I'm just putting it as T. Housing typology.
spatial.
Housing typology is spatial, correct. And build up area,
That is also spatial.
spatial. Because with time, your build up area is not going to change for I mean, if people are moving from a different house to a different household, that's a totally different context, and that's again spatial because you're again shifting or you're upgrading. So, but in general, housing typology or build-up area is a spatial factor. So the answer is C and D. So these two factors contribute as explanatory variables for predicting spatial variations. Right. Now let's go to the next question. Oh yeah, so this is our question 13. Per capita consumption for industrial demand for a city is, so this is again a direct application from the NBC, which is given. So what do we take as a per capita for the industrial demand for a city? Any guesses? You can guess. I mean,
50.
okay, somebody says 50. Any more guesses? I guess everybody can just simply guess no, any, because it's an industrial demand city, so which means it needs some, uh, like it needs good amount of water. So somebody says 40, okay, good. So 50 and 40, fine. No other guesses, so let's look at the theory. So this is what we learned. So for yeah, so institutional and commercial water demand. So in highly commercialized cities, we usually take it as 50 is what is said. So yeah, so 50 is the answer for this one. It's option C, 50. Right, it's not 40, it's 50. Okay, let's go to the next question. Dash percentage of what total water consumption accounts for water loss due to bad pumping, defective joints, damaged water meters, unauthorized connections, etc. So based on all these defects, how much percentage of water is lost in the water? Yes,
15%.
15. We just saw that right now in the previous one. So yeah, so just going back here. So we have it here. So 15 percentage of the total consumption is lost. So this is from this particular source. So yeah, so that's the answer. Let's go to question number 15. Dash scheme is associated with the provision of piped water supply to every household. Yes, any
Nal se
guesses?
We
Nal se
Nal se
jal.
Jal.
Okay, Nal se jal, fine. So what does this Namami Ganga does?
It is for cleaning and setting up of STP to the Ganges and adjoining rivers of Ganges.
Correct. Yeah. So it's for cleaning Ganga and tributaries. Now, what is this? What does Nirmal Dhara and Aviral Dhara does? Like, what is that for?
Nirmal Dhara.
Okay, that's mainly for rivers, like regeneration of rivers. Both of them are used to regenerate rivers. So yeah. So the answer for this is Nal Se Jal.
Could you be more specific about which river? If
Uh, okay, that I need to check, but in general, it's mainly used for regeneration of river. Which rivers it's been currently implemented in, I'll get back. I'm not really sure where it's being done. Okay, so that'll be there in Google also. Yeah, I can tell you by the end of the class also. So yeah, so let's go to the next question, question 16, which is the wrong statement concerning urban water supply. Water supply is a central subject. Center oversees the interstate distribution of water. Swachh Bharat mission is associated with urban waste management and sanitation. Jal Shakti Ministry aims to provide piped water supply to every house by 2024. So it's regarding urban water supply. So let's go by from the last option. Option D, Shakti Ministry aims to provide pipe water supply to every household by 2024. Is that right?
it is right, madam.
It is right.
Correct.
Yeah, we have discussed this. It's right. Now, option C, Swachh Bharat mission is associated with urban waste management and sanitation.
Right.
Right, that's also
Correct.
correct. Center oversees the interstate distribution of water. Is that right?
Yes.
Yes. Yes.
Correct.
Right.
Now, water supply is a central subject. Is that right?
It's a state subject.
It's a state subject. Correct. So this is wrong. So the correct answer is A. Water supply is a central subject. That is the wrong answer. Let's proceed. Block tariff is an example of dash. Volumetric tariff, fixed tariff, two-part charge, indirect cost. So yes, so we learned about different types of tariffs. Okay, let's try attempting this question. Any guesses for this one? Block tariff.
A volumetric.
Okay, a volumetric. Fine. Let's look at the theory also. So this is what we learned in terms of tariff design. So we have fixed charge, we have volumetric charge, and then we have two-part charge. So basically, we have a fixed, and then for every volume, we are considering, we are adding more. So fixed charge means it's a flat rate, or based on the by ferrule base means based on the diameter of the pipe, based on the amount of water that's there. So it's not metered, but it's a fixed flat rate. But if it's a volumetric rate, for every volume, every cubic meter we are consuming, we have to pay for it. So that's the flat cubic meter rate. Then we also have block tariffs where you have a block for certain volume you consider this much. Then you move on to the next block. So for 100 to 200 cubic meters, if you're considering, then you pay this much. But if the minute it goes to 300, then it goes to the next block. So that is a block tariff. And in block tariff also you can have an increasing block tariff. That is when you're consuming more, then you are paying more for it. When you're moving to a higher block, then you're paying more for it. And you can also have a decreasing block also, and you consume more, you're paying less for it. And then of course you have the two-part charge where you have a fixed charge, which is the base, and after you reach the base you go for a volumetric charge. So here again, so all this block tariff mainly comes under volumetric because it's based on the volume. So that's what was asked. So block tariff is an example of volumetric charge. So we also discussed what are fixed charges, what are two-part charges, and what is indirect cost. There's direct cost and indirect cost in water supply system. So what constitutes the indirect cost? Any observations? Yes.
Indirect costs are uh,
Yeah, so we learned about different costs. So we have direct costs, which mainly in direct you have fixed and variable cost, where you have the initial capital investment which is there, and the interest, all the life cycle analysis, everything. Then there is a variable cost that is every recurringly that we'll have to, like power, bulk water supplies, everything. In addition to those, there's always an indirect cost also, which talks about all the administration charges, establishment charges. So all these policy intervention charges, all these directly, like, or it's not very tangibly visible into this, but these are also part of the overall cost that is invested in our water supply system. So when we are considering about cost recovery, we also need to look into this indirect cost which will be incurred over time also. So some establishment charges, administration charges, all these will come under our indirect cost. Right. So we are proceeding on to the last question. So I think we went really fast today. So this is the last question. Uh, it's a match the following. So let's go by option by, I think, yeah, we'll go one by one. So manpower cost, what is, which of, what is the basis of defining manpower cost?
I guess bullet number three based on number of employees.
Yeah, manpower, because none of the other options talks about people. So yeah, so it is bullet number three. Yeah, so it is based on the number of employees. Correct. Bulk water rates. Anybody?
Serial number one,
Serial number
cost to
one.
acquire water.
Correct, yeah. Because this is the only option which talks about the cost required to acquire water, and it's the definition of bulk water rates also, from the cost required to acquire from urban local bodies for from source what yeah cost to acquire water from source by urban local bodies from the state local bodies. That's the definition. Correct. Now options the sorry bullet C, chemical or treatment cost. What will that depend on? There is only one option which talks about water treatment.
Option two.
Two.
Two, yeah, it depends on the water which is treated. Because based on the amount of impurities which is there, amount of quantity of water which is treated, all the cost will vary. Repair and maintenance cost, it depends upon the cost on major replacements, for example, major and periodic maintenance, everything. So that works out to option A, right? 3, 1, yeah, option A. 3,
A.
1, 2, yeah, option A. Right. So yeah, so that's it. That's all the questions that I have. But we have time, so if you have any doubts, we can discuss those regarding this week two's lecture. I guess somebody had asked a doubt about fire demand calculation last week, right? Is that sorted? I think it was.
I think he was asking about that assumption we took for that.
Ha, right, 1,000. But I think this time's question paper we have meant it's mentioned, no, how much is to be taken, or it's not mentioned. The assumption is not mentioned. I was under the
Not
impression
mentioned, I think.
it's not. Oh, okay, fine. Then it would be clear right now. But yeah, sometimes they will give, like in some textbooks, I've seen that they will already give the value. So the value like 1,000 liters per minute. So if it's given, then we need not worry. But if it's not given, we usually take 1,100 liters per minute. Right. So yeah, so you can I mean, since our time is there till 9 o'clock, I'll be there till 9 o'clock over here. If there's some doubt, you can always shoot, or you can always discuss, or if not, I think you can leave also, because the questions, we are done with the questions right now.
So can we leave now then?
Yeah, you can, if you don't have any doubts regarding,
Yeah.
yeah, you can leave.
Okay.
Thank you very
Thank
much
you.
for
Thank you.
attending. I will be there till 9 o'clock in this platform in the same link. So if there's any doubt, you can always join back and ask also. So the session will go till 9. Yeah, thank you.
Thank you, ma'am.
Yeah.